This video is about electrophilic substitution in benzene. So let's just look at the word electrophilic substitution. First of all, philic means to like. Substitution means you are replacing something. And electro means something that's sort of negatively charged, or electrons, electrons. So it means something that lights a negative charge or electrons is replacing something else. Well, first of all, let's just look at representations of benzene. There are two ways. We can use the AQA structures, which are resonance structures to show this kind of an average thing here, where the electrons move around with double-headed arrows throughout, and these two resonance structures. Or we can use this structure here, where you've got the hexagon of the benzene carbon-carbon single bonds, and this electron density being delocalized, shown by this circle. And you can do mechanisms with either on most exam boards. Please look at your specification to make sure. I will try and use the AQA one, however I'll show you a little bit of this one at the end. Now there are three steps to this type of reaction. First of all is using a catalyst to create the electrophile. Then there's the mechanism, the reaction mechanism, and then there's regaining the catalyst. So we look at the first step, which is using catalysts to create the electrophile. So catalysts lower the activation energy of reaction, which allows the highly stable benzene molecule to react with something because it forms this electrophile. The first one, if we're reacting with bromine, we have the catalyst here, or here, FeBr3 if you're bromine, or AlCl3 for chlorine, reacts with a molecule, forming FeBr4-, one of the bromines broken and one's gone off to there, or AlCl4-, plus the electrophile Br+, or Cl+. What we can also do is we can use AlCl3, another common one that you'll come across at A level, plus this molecule here. We'll go to AlCl4- plus this tertiary carbocation here, with a positive charge on that central carbon. Now, they're common catalysts used to get those electrophiles. Now let's look at the general mechanism. Now the general mechanism for this is this electrophile is attracted to the electron density of the benzene molecule. So what can happen as it approaches the benzene, one of the bonds in there, if you're using the AQA structure, some of the electron density goes towards there and sends a pair of electrons to form a bond with this electrophile here. That forms an intermediate. And again, sorry if I'm drawing bad hexagons, as I'm not an artist, I'm a chemist. Now you get the hydrogen on here, you get the electrophile, which I'm just calling X, being bonded to there. Still got these bonds if you're using the AQA structure. Now you've got positive charge on there. What happens? It has two choices. You could have something else, so say a Br- could come in and attack via addition, or this bond on the hydrogen could go back in and form the pi system M. Well, what's easier? Well, it's easier to break this bond and give out a proton, because the bonds are just closer. They're there. You don't have to rely on things colliding with the right activation energy and stuff like that. And that's why we get a substitution rather than addition. It's just easier to happen, really. And still got the X there. The bond between the carbon and the hydrogen has gone over, donated 2 electrons between the 2 carbons, and sort of a proton is given out. So that's your general reaction mechanism, where X plus could equal Br plus, Cl plus, or just any other thing that you're using, such as this tertiary carbocation. Now, we have to regain the catalyst at the end. So we have this proton that's given off, H+. We have something like FeBr4-, and what can happen is they can actually react to form FeBr3, which was the catalyst, so the catalyst is regained, and HBr. And that's effectively what we can do, and the same thing happens with the chlorine version of the reaction, AlCl4-, reacts with the proton to form AlCl3, catalyst is back, plus HCl, and that's how we regain the catalyst of a reaction. Now let's put all the steps together in an example. So reacting it with bromine, well, we need the catalyst. FeBr3 is a very good catalyst for this reaction. This reaction will probably take place in an aqueous form as you're getting ions. We react it with bromine in aqueous form. That should be a Br2 molecule, and that goes to FeBr4 minus, aqueous, and Br plus in aqueous. It's brilliant. We've formed our electrophile using our catalyst. Now that can react. So we have our Br plus electrophile here. Double bond, double-headed arrow representing 2 electrons comes here, attacks the bromine. That forms this intermediate here, where you've got your hydrogen still on the carbon, and you've got your bromine on the carbon. Now this bond can break and go between the 2 carbons, leaving the pi system intact once again, and that has a positive charge on there. But now it's been substituted, the hydrogen's been substituted for the bromine, and the proton comes out. So the pi system's been remade, it's been broken, it's been remade, so it's a lot more stable once again. And now this proton can attack the FeBr4 minus molecule and form the catalyst back again, FeBr3 and hydrogen bromide, which that all takes place in solution once again, so don't forget the state symbols when you're writing it out. So this is an example using bromine. That's nice and simple, and everything's like that. Like I said, you use chlorine, or if you're doing something like an SL chloride reaction, you can do the same thing, just with the correct catalyst. That's all for this video. It was a nice short video just to show you the general mechanism behind it all. Please share this with your friends if they're struggling with a topic. Like and subscribe for more videos, and let me know if there's any topics you would like me to cover that I have not already. Thank you.